Friday and then spring break. So, homework is due on Friday, and we're going to continue talking about hypothesis tests today. On Friday, we'll talk a little bit more of interpretation, talking about hypothesis tests and what they mean, and a few other subtleties about that kind of go beyond a little bit beyond what we're doing in the homework. We're not going to talk about a couple versions of hypothesis tests. We're not going to talk about things with variances or something specific for the Poisson, but we'll get the main idea of hypothesis tests. And on Monday, we do things with means, hypothesis tests about a mean of a distribution, and we'll do a hypothesis test about a proportion today, right? Which are two of the main ways that we do it. After spring break, we come back and we'll look at comparing two means, comparing proportions, and then move on to other inference procedures. But any questions about things or about the homework? Have you been looking at that some? Right. So what do you remember about hypothesis tests? What are we doing in hypothesis testing? What do we hope to accomplish? So seeing if there's a difference, yeah, right? So we had a null value, some idea of what the situation was, and we get data. Does our data line up with what we thought the world was like, or have things changed? Right? So in this case, we're going to look at a proportion. Maybe we have an idea about the proportion from the past. Maybe we have some theoretical idea based on science, what it should be. Maybe there's genetic argument about how things combine and rates in the population. But anyway, we're interested in that. We're going to collect data. And is there a difference, right? So if our data, why did we reject it a hypothesis? Our data doesn't look like what it was before, right? And it looks like things have changed. And it's surprising enough, it's a big enough change, right, we're going to reject, right? So we're going to do that specifically for this case. So kind of general picture, right, that applies to this one as well. We have some population, and we have some proportion we'd like to know about in that population. We're going to have some hypotheses about that. Is it a particular value? Versus maybe an alternative that it's not that value anymore. We want to be answering this question. Is it still p sub 0 or have things changed? And so to answer that question, we're going to take our sample. We're going to have n trials. We're going to get a certain number x of successes. And our sample proportion p hat is going to be x over n. And we start out with a null hypothesis. If p hat's too far away, here's p sub 0, and here's p sub hat. Is p hat too far away? To believe p sub 0. If p hat's too far away from p sub 0, that null hypothesis that it is a certain value doesn't make any sense anymore, and we'd likely reject it and move on to thinking about things differently. Decisions about treatments or investments or whatever, decisions about plans, assuming that things have changed and justify that change. So but the crux then is deciding what's too far away. Just because something is 5% away, maybe that's enough, maybe it's not. It all depends on, well, the sample size, but more specifically, the sampling distribution, right? What values of p hat are likely. So under the null hypothesis, when p equals p sub 0, well, we know a lot of things, that if x is binomial, it's binomial random variable. We know that the expected value of x was within times p variance of x, we had a formula for that. It was n times p times 1 minus p. P hat now is x over n. And we're counting the number that have a certain characteristic over n. Our probability theory says that the expected value of p hat should just be n over the expected value here, so it's p. On average, our sample proportion should give us the population one. The variance of p hat, well, when you divide by something, you get that square in the base of the variance. So you get p times 1 minus p over n ends up being there. The central limit theorem tells us that p hat is approximately normally distributed. It's centered at p with a variance of p times 1 minus p over n. So we know a lot about the distribution about p hat from probability theory. And then once we have this assumption about the null, right? If H0 is true, right, p hat should be approximately distributed like a normal random variable centered at p0 with variance that's p0, 1 minus p0 over n. Right, so we should both know the average and the variance, right, if that null hypothesis is true. So to calculate the probability whether p hat is unusual, we have a distribution to use. Yes?
Where does that big N come from?
Where does the big N come from? So this is this little abbreviation for central limit theorem. Right. And so that I mean that it's a normally distributed. Whoa. I'll try to rewrite that again. All right. So that the p hat sampling distribution is approximately normal. That the binomial, it counts at certain points, but if we get a big enough sample size, those points start to look like a bell-shaped curve. So probabilities calculated either with the normal approximation or the actual ones are pretty good. So we're going to use the normal approximation for K area. So if you have p0 here, p hat, we're going to calculate the probability that maybe we're going to calculate a value to convert this thing to the normal scale. Centering at 0, we're going to calculate a z value. That standardized value is we're going to subtract the mean of p0 and then divide by the standard error. So p0, 1 minus p0 over yeah, all that. And then we're going to calculate the probability we're bigger than that z or less than that z under a standard normal. So let's look at an example. Right? So let's say that it's stated that 9% of the U.S. population lives in poverty. Poverty rate is stated to be 900, 9% of households. There. And then a sample of 500 households. And the rate in these households is about 11%. 12%, 0.118. Samples. is it reasonable just to stay with the statement that 9% are in poverty, or is this sample inconsistent with that? So we want to set up some hypotheses, right? That P equals something versus P does not equal something. Which of the values do we want to use as our null hypothesis values? Which one? Yeah, the ones that we're giving these couple numbers, right? But so one of them is going to be the one that we're equal to, right? And one's the sample. We always do the hypotheses about, kind of the general claim, the status quo. So 0.09. So this could be asking the question, is 9% accurate? Are the data consistent with 9%? So we're going to say, what's the probability that we get a p hat greater than or equal to 0.118? There's a chance that we get something that we have or is bigger, kind of that direction. This is the probability that is normal. Right? 0.118 is our sample. 0.09 is the hypothesis, the null value. And we divide it by the standard error. So 0.09, 0.91, 1 minus that. And we had 500. We're going to get this probability that this is greater. This difference is 0.028 in the top. The standard error from a sample this size, and that's 0.013. And so it's the probability that a normal is greater than 2.19. If we look up 2.19, so on our normal tables, we would do it as less than 2.19 because our normal tables get less than values. Here's the normal table. We're going to have 2.19. Here we put probably that's less than that. So if we go to the normal table and go under 2.19, 9857 is the value we would look up. So that the column header here was a value and a probability. Go away. So the value we had at 2.19, there is 0.9857. So 1 minus 0.9857, 9857. So that's 0.0143. About 1.43%. The chance that we actually get something at 11.8% or more, if it really was 9%, is just about 1%. So I'll draw a picture of that. Yes.
Why are you doing 1 minus?
Well, I really want just the chance that it's bigger than that, right? And then our tables only get less than, so it has to be 1 minus. Let's draw a picture, kind of help with a couple of things here.
Could you go back to 1 page?
Yeah, sure. I'm going to draw a picture where we're centered at 0.09, and then start 0.118 here, and we're calculating this area kind of going up there. That's the picture we're looking at. And this is this calculation down here. So we take our sample point. What's the probability we would get something like 0.118 bigger? 0.09 is the real thing. We're going to subtract the mean, divide by the standard error, appropriate for 0.09. It turns out that we're actually 2.19, 2.2 standard errors above. Being more than 2 standard errors usually is kind of unusual. There's not that much probability, right? 1.43 is the probability of being out. Right? So in our picture, here was the null value, p equals p0. 0 is 0.09. This is our p hat that we've gotten. The sampling distribution, because our sample size is pretty big, is pretty close to normal. And we've standardized things. So for a standard normal, here's a 0. This thing corresponded to 2.19 standard errors away. And matching that up. And the chance that we were bigger than that was just about 1.5%. It's something that happens only 1% of the time, or maybe 2% of the time. Is that a common thing? Or kind of unusual, kind of surprising? Not something you expect every day. So because the 0.0143 is small, we are going to reject the null hypothesis that said that p was 0.09, and we're going to conclude that p, the poverty rate, is larger. Because we have a small thing out, probability out there, a small chance. It's not something that's going to happen every day. It's mostly inconsistent with the 0.09. And it's small enough. A little more specifically, if we set up the hypothesis to say that it's just, is it 9% or not, really getting something out here or bigger is surprising. But kind of on the other side, going to an equal tail out this way and back would also be surprising. So technically what we do is calculate the p-value. In this case, it's 2 times that tail area. So 2 times the 0.0143 times 0.02.86. 2.5, almost 3%. And we reject the null hypothesis. In this case, because the p-value is small, we often set up a standard called a significance level. Say 0.05, the significance level is usually called an alpha level. And because our p-value is less than 5%, right, that's a decision standard, we reject. So we reject H0 because the p-value is less than 0.05. So what would be the smallest value of p hat for which we'd actually reject? Right? This one's kind of clearly beyond the level, right? Beyond 5%. It's not that point. We can figure out where's that limit, how far away. Now, it could have been closer. It could have been 0.117, 0.116, and probably still would have been a small enough. Reject, where's the limit? Where do we reject the null hypothesis that p equals 0? In this case, it's 0.09, 9% poverty. Well, for that, it's centered here at p0, 0.09. We want to find the places, say that we're going to do this at 5% level. We want to find the places out here that just have 2.5% of the tail. What is this? What is this value out here? If we're out past that, that's going to be surprising to us. Rejection is out here. Or if if our hypothesis is two-sided, right, we don't care, is it bigger or is it less? If they're both evidence against this 0.09, we're to reject, right? So for a standard normal, we've encountered that those 2.5% tails are about 1.96. So for a standard normal, 0, 1, that's centered at 0, mean of 0. And about 1.96 has 2.5% above it, and then negative 1.96 had 2.5% below it. When we first looked at confidence intervals and things, we did plus or minus 2 standard errors. That's kind of an approximation to the actual normal when we look at the table. We get about that. So if you translate from standard normal into the distribution P hat, right, we want, we take P0 plus the 1.96 times the standard error. Right, so P0, 1 minus P0 over N. Let's go this way. If P hat is above that, it's going to be out in that little tail, right, and be surprising. Or if P hat is less than P0, minus the 1.96. P0, 1 minus P0 over N. And so under this hypothesis that it's 9%, 0.09 plus 1.96, 0.09, 0.91, there were 500. The sample there. This lower one, 0.09 minus 1.96, 0.09, 0.91 over 500. And this lower limit is 0.0645. Right. This upper one was 0.1155. So if our sample proportion had been, 0.1155 or above, we would reject. Or if it had been that small. Both of those would say that 0.99% is not realistic. And we would have taken a real change. If that was really a random sample of a population, then that poverty rate would have been really higher. Right, they reported the unemployment rates for the nation and for Vermont just recently, and Vermont hit kind of the lowest unemployment it's had since the 1970s maybe. Right? 2.5% of the state, incredibly low. Some places are closer to 1%. Some dairy was 5% or something, right? So those different ones are based on samples. And every little location there probably is not a very big sample to determine that. So maybe they're different, maybe there's just sampling variability if it's based on samples, those rates. But any questions around some of these things? Well, let's do another example. Let's get this clear what to do. Sure. So, for treatments for baldness, Rogaine is supposed to help about 40% of men with hair loss. Increase in hair to a noticeable degree. Last year, they reported a new treatment for that called that it contains an ingredient called dimethylpolysiloxane. And let's say it's applied to 270 improvements right out of that. So the sample proportion point was 0.431. Is this, if this were the sample, and you had these data, would this prove that this new treatment, that new chemical, had a significant improvement? Significantly better than what was before. It's significantly above 0.4. Is the new treatment better? So what are our null hypotheses? What are our hypotheses?
The new treatment and the old treatment treat the same percent of people.
So this is going to be the same. Is going to be the. Jeez, the screen is going to go okay. Is it the same? So what does that mean that the proportion is if it's the same? We want to write P equals something.
P equals 0.4.
Yeah. So I'm reading these story questions. There's going to be a sample proportion, there's going to be a population one, or some value told to you. You want to find the one that's told to you is kind of the fact or the status quo, what's been done before. We call that the null. And this one, let's try a one-sided one where is it better? If it's worse, we're not going to market it. Right? If it's better, significantly better, then yeah, we can go ahead with that. Well, we can calculate a z statistic, shall we do that? Right. So we'll calculate that z p hat minus p0 divided by standard error, p minus 1 minus p over n. So we put the null value in there because that's the null assumption. So our sample was 0.431 minus 0.40, and 0.40, 1 minus that is 0.60, and 270. And that, these statistics, this is about 0.031, this is about 0.0298, and so it's not much more than 1. It's 1 something. What is it exactly? Not sure what it is exactly. But it's pretty close to 1. It's a little bit bigger than 1. Is a z value of 1 going to be surprising or extreme?
I think it's 1.04.
1.0. Right, so we have here 0.40, right, 0.431. If this is really the distribution at the null hypothesis, and this is our p hat, what's the probability we're up here? So the probability that our sample proportion would be greater than what we have, equal or greater than what we have, is the probability that a standard normal is greater than 1.04. If you look at our normal table at 1.0, what is that? 1.04 is going to be down in this row. 1.04 here. It gives us that percentage 0.85, 8508, but that's less than that. So bigger than that is about 0.15. The chance that you're bigger than that is about 0.15. So that's this tail area over here. If we're only interested in looking in this one direction, and we've really kind of done the preliminary studies to show that maybe this actually works, and we really believe it's going to be better, right, and we really, our alternative is just this one-sided. We're just going to call this one-sided p-value. And is 15% terribly surprising? Is it a really rare phenomenon? not so much, right? It's not 5%, it's not 1%. Things happen, you know, things that can happen 15% of the time happen pretty regularly, right? A few days or so. It's not so extreme. So we would say, because this p-value is greater than a standard like 0.05, do not reject. Hypothesis. For this particular treatment, then, it is not significantly better. Yes, the sample proportion was a little higher, but given that it was only on 270 people, we can't say statistically that it's not just due to chance. The new treatment. It's not statistically significantly better. So it's not convincing. You need to be out a little bit further to actually be sure that it's not just a random chance that we got kind of a high sample of 0.431. Maybe it's still 0.4. We just happen to get a slightly higher than average result. It's within the realm of random possibilities. How big would it have to be if we? When would we reject? When would we reject? When would we? In favor of the alternative that says p is greater than 0.4. Well, if it's going to be far enough away, you know, you get a p hat out here such that there's only 5% out here at one side of it. If our p hat were out there, not at 15% back here, but out at 5%, then it's getting bigger, it's more surprising. What's that value? Well, p0. Now the normal value, the z value that we use for this one-sided thing is about 1.645. Why that one and not 1.96? Well, where does that show up? So if you look at where is about the 95th percentile. The 95th percentile is just about here, right? So we have 5% in the tail, that leaves 95% behind. All right, so we're looking for the 95th percentile. And 1.64, 1.65 is kind of right in the middle of those. So if it's one-sided, we use this 1.645 as a cutoff. So if we do that, we're going to put the z value times the standard error. So we're just going to look at one side. If it's bigger, that's all we care about. So 0.09 plus 1.645, 0.09. I'm not talking about poverty anymore. 0.4, 0.4, and this one's 0.4, and so 0.6, and a sample of 270s. Right, so if it's greater than that, then it would be far enough out. Do I know what that is? Let's count that one real quick. Put that number in there. Right, so 0.4 plus the 1.645 times standard error, so 0.4 times 0.6 over 270, 0.449. So if we had got a proportion that was over 0.449, if p hat's bigger than that, that's going to be enough. And then we're going to reject because it's out past the 5% cutoff. You didn't. This treatment was kind of surprising. It's actually the ingredient of McDonald's French fries. So I don't know how they came up with that, but in the case. I don't know what that means, if you allow me to, but it's a chemical that's in those things, but it seems to have some funny effects on the body. So, in any case, so if we had a sample proportion that would be out there a little bit further, all right, then we would reject. But any questions about doing this hypothesis? What affects our chances of having a significant result? Yeah.
Population size.
The sample size in our population, you know, you can hear the sample size, right? The difference between the sample value or the population value. So you can change a few of these numbers. Let's say we had 2,700 as our sample size, right? And p hat, again, is 0.431. Same null hypothesis. 0.4 versus an alternative greater than 0.4. Or are you going to reject this one? Is this going to be enough evidence to reject that null hypothesis? Well, now we reject the null hypothesis if p hat is greater than, still p0 plus still that same z value in there. P0 minus p0 over n. So n's going to change in there. So 0.4 plus 1.645, 0.4.6 over now 2,700. That's going to be, how much is that going to be? Right? So that's basically the code I had before, but with an extra 0 in there, 0.4155. Now 0.4155 is going to be enough. So this is 10 times the sample size. If I had 10 times the sample size, it still stayed away from 0.4. It's more convincing. In terms of the picture of the sampling distribution, when n was 270, so you're here at 0.4, it's like this. But when I get 2,700, then the sampling distribution is really narrow. So our 0.431, under the small sample size, there's an easy chance of getting out past that. But when it's a big sample size and everything is, if 0.4 were true, everything would be really close to 0.4. The 0.431 is far enough away. So here we reject H0 because we're beyond that point. What's the z value associated with this thing? Right, so p hat minus p0. P0, 1 minus P0 over n. So it's 0.431 minus 0.40, 0.40, 0.60 over 2,700. Dividing by 2,700 in the denominator is like multiplying by the numerator. Right? So as this gets bigger and bigger here, it's like having a bigger number multiplied on top. That statistic is. Right, so 0.431 minus 0.40 divided by the standard error, 0.4 times 0.6 over 2,700. 3.29. The z value of 3.29 is out there, right? 3 standard errors away. That's larger than 1.645, larger than 1.9, any of these standard values. Z value is far, so large z value. Rejectable hypothesis. But any questions? So one thing about interpreting hypothesis tests versus confidence tests. So we've done we drew the same picture of a cloud with the population P, and we got our data, right? And we did confidence interval one way, and we did a hypothesis, right? So both of them have the same goal of telling you about the population. So it'd be nice if they told you the same thing, right? If they're consistent. And in fact, they do. Right? If you do a hypothesis test, P equals P0 versus the alternative that is not that, and you do this at a certain significance level, that 0.05 is for significance level. So we reject P0. Our p-value, right, is less than alpha. You do that, or you do a confidence interval for p. P hat plus or minus, well, two-sided, 95% confidence interval. So 95% confidence interval for p. And then you have p hat 1 minus p hat over n. That, so 95% confidence level. Use the corresponding significance level to confidence level. Any value that's covered by the confidence interval, just about any value, would not be rejected as the null hypothesis. The null hypothesis is any value that's covered by this interval, you know, p hat in the middle. Any value of p0 that would be in that interval is going to be okay. We're not going to reject it. And anything we don't reject would show up in the confidence. And the counterpositive is true. If you get a p hat, you reject it, right? Then that confidence interval isn't going to go all the way over to p sub 0. It's going to miss it. So the idea is if the null hypothesis is true, we're going to, we're going to reject out here. Picture, all that stuff. You get p hats that are going to be outside of there. The intervals that you're going to draw for like a confidence interval corresponding to that, any p0, any value of p hat that's in that rejection region, it won't quite stretch over to that. So there's kind of a one-to-one correspondence. If you see a confidence interval and it doesn't include a value, you're going to reject it. And anything that's in the confidence interval, you can't reject. There's a little wrinkle here that it changes just a little bit for proportions, because in one case you use p hat, and the other one you use p0. So just right at the margin, there could be like one or two cases where it's just right on the edge there, but and it doesn't work like that. But basically, it's a correspondence. So in this, so another hair thing for growing hair, Nutrafol has a success rate of about 0.35. And if we get our old 270 to our new treatment, p hat is 0.431. We do 95% confidence interval for the value of p, using the new treatment. Our 95% confidence interval, p hat plus or minus 1.96. P hat 1 minus p hat over n. Now like p 1 minus p over n, but now at the sample point. So 0.431 minus 1.96. 0.431. 1 minus that is 569 over our 270. And our interval, did I do that one? and work problems, and then I decided to do them kind of a different way sometimes. Let's put that in to the computer. Keep that up there. Type something over here. You can kind of see that. Oh, it's small. So 0.431 minus 1.96 times the square root of 0.431.569 over 270. And that number, right, plus. So 0.372 up to 490. 372 up to 490. That's the 95% confidence interval for the new value of the success rate. Is it plausible that it's still the same as the old one? 35%? No, I mean the confidence interval doesn't include 0.05. So, if we had a hypothesis, 0.35 versus an alternative that p is not equal to 0.35. Just based on that interval, 0.35 is not reasonable. It's not in the 95% confidence interval. It would have a p-value less than 0.05. Reject H0 because P0 equals 0.05 is not covered by the confidence interval. So it's probably significantly different than that. So if you just have a confidence interval and you're asked about hypothesis tests, you can tell directly. And so, on an exam, if I ask you to test, whether it's the same, you can make a confidence interval if you want. And then say, because the confidence interval doesn't cover that value, we reject it. So we have these two ways of doing inference, and really they do the same thing. At the core of both of them working is that sampling distribution of the statistic. P hat in this case, on Monday it was X bar, but it's a sampling distribution of that and looking at the standard error. And where is your estimate relative to the null hypothesis in terms of how much standard error away? That's principally what we have to do for today. But any questions about this or homework? Stop just a bit early. Do you have individual questions you want to ask about things? Do that, and we'll do more with interpretation, more examples and things on Friday.
So I have my presentation date for
Okay.
that project. It's going to be April 16th. So that's just going to be like 30 minutes of discussing the topic is what I've been told.
Okay.
This assignment. And then as the semester goes on, I think it's May 1st or April 30th is the day that I have to pass in like my formal paper.
Okay.
So I think it'll probably get I'll probably get going on it like more steadily as break ends. But So maybe sometime that week when we come back, I'll meet with you. and
Okay.
We can, I'll just talk to you about like kind of what I've been
Okay, sounds good.
going on and then any insight.
Yeah,
you
you
have.
know, try to work with the computer and then have
Yeah.
questions about that.
Perfect.
So.
Anything I have with what
Yeah. Wait, come
come
grab
up
his
with over
stuff.
break or
Come grab it.
when we get back, I'll just kind of show you and see what you think of it and
Okay.
move on, but I appreciate it, and then, oh wait, we have class Friday. I was gonna say have a good break.
Oh, yeah.
Not just yet.
Yeah. Tegan left your stuff, huh?
Yeah, I did.
Well, you can come back and get it. Surprise, we're gone, so. It's all right. I don't need to leave things in this room afterwards.
All right, have
Yeah,
a good one.
You too.